Vice President, Director of Research, and CEO of the Rocky Mountain Institute. He's a MacArthur Fellow, was educated at Harvard and Oxford, recipient of 6 honorary doctorates. He has consulted, analyzed, and lectured on all issues of energy and resource policy in over 30 countries. Formerly was Regents Lecturer in Resource Policy and Economics at the University of California, lecturer at the University of British Columbia, as well as a distinguished visiting professor at the University of Colorado. Now I shortened this, so I would cut too much into his time. He has advised and consulted for many organizations, several hundred utilities, developers, financial houses, and governments. He has been an advisor to the NARUC Conservation Committee, won the Alternative Nobel, as well as the Onassis Prize. His key issue throughout his research was how can we use energy more efficiently. And I guarantee that all the electrical fans around here is most energy efficient. We are going to tape this session, so those of you who may want to review it will have a chance to see it on videotape at some later point in the course. Or if you would like to switch after half to another parallel session. Thank you very much for coming, Amory. It's my pleasure to have you here.
Thank you. Yeah, the videotape's a good idea. They say it makes more sense the second or third time anyway. I'm not quite sure how long I've been doing this. It must be about a decade. There is always more to say because the revolution in wringing more work out of each kilowatt hour continues. It has already gotten well into 6 transitions, namely appreciating that market failures do happen. The world is not a paradise for the sort of economic theorists who no doubt lie awake at nights worrying about whether what works in practice can possibly work in theory. I think most people now appreciate that the energy problem is not simply where to get more energy, more of any kind from any source at any price, but rather how to get the amount and type and scale and source of energy that will do each desired task in the cheapest way. That is, what we're after is not kilowatt hours or barrels of sticky black goo, but things like hot showers and cold beer, the purposes for which we want the energy. And that so-called end-use least cost approach, asking what's the job, what's the best tool for the job, has turned out to be a very fruitful way to think about energy and many other problems. Initially, efficiency was focused just on the residential sector. It's now moved particularly to commercial and industrial, where most of the biggest and cheapest savings are, although there are attractive candidates in all sectors. Initially, people just tried to affect when electricity was used. That saves capacity. And then they realized that if they do end-use efficiency, saving it all the time whenever it's used, then they'll save capacity and fuel and pollution. And it's better in general to get 3 benefits than 1 benefit. Load management still has a place, but by the time you get through with efficiency, there's not much load left to manage. Initially, a bunch of folks claimed savings without measuring them. Well, in God we trust, all others bring data. And by now there's a very well-developed art of measurement and evaluation. It's often more elaborate than it ought to be. But there are some very good results out. I would particularly call your attention to the California results being released this week, which show typically matches within a few percent between predicted and actual savings. That's the way it ought to be. There is a well-known and very good article by Nadell and Keating in the Chicago Evaluation Conference some years ago, which folks like Paul Josko often quote as saying that measured savings are typically far smaller than predicted savings. That's the opposite of what the article actually says, so I hope you'll read it if you run into that in the literature. We've been moving also in the regulatory arena from sticks painted orange to real carrots. That is, from simply trying to cajole or threaten utilities into helping customers save electricity to, of all things, rewarding them when they successfully do so. Now, I'm going to talk very little about those things, but rather about 6 new transitions. One is the transition in engineering from fragmented electricity-saving measures generated by slice and dice, line item, spreadsheet kinds of software to integrated packages with real optimization. Another is from working on equipment to working on the application first and then the equipment. I'll probably say a little about moving from engineered delivery, the we will wrap your water heater approach, to market making, making saved electricity into a commodity. And I'll hope to get time to say a little about how the economic and engineering models we often use to try to predict how people use energy are not simply seriously incomplete, they're often actually misleading. They're telling us the opposite of what people do in using energy. And I will undoubtedly be saying a bit probably in the second part about moving from promoting hardware to correcting market failures, for example, by reintegrating the design process using optimization instead of obsolete rules of thumb, and fixing perverse incentives that reward people for wasting energy and penalize them for saving it. You will find this is very common in the building sector. And I'll try to say a little bit about counting some enormous side benefits like increased labor productivity that often come with properly done energy efficiency and can be worth about an order of magnitude more. For a little context, there are really 4 revolutions going on in efficient use of electricity. They're all interactive, they're all important. One is on the technological front. Most of the best ways we have to save electricity now were not on the market a year ago, the same was true a year ago, and so on. In fact, it's been true for probably the past 8 or 10 years that in each year you can save about twice as much at a third the cost that was possible 5 years earlier. In recent years, this has been not so much because of better widgets as because of better understanding of how to combine them. I'll get into that in a minute. At the same time, there's been equally rapid progress in how to finance, market, and deliver technologies to customers, whether through utilities or through private actors. And that has come along with reform in utility regulation on the lines unanimously agreed by NARUC in November '89 to make the least cost investment for society into the utility's most profitable investment and the most costly investment into the least profitable. In that way, customers and shareholders' interests become aligned rather than opposite, and typically this is done in 2 steps, both of which are important. One is to decouple utilities' profits from their volume of sales so they're no longer rewarded for selling more energy nor penalized for selling less, as they would be under traditional rate of return regulation. And secondly, if the utility does something smart to cut your bill, you let them keep part of the saving as extra profit. So they have a piece of the action. It can be a pretty small piece and still get their attention very clearly. As John Rowe said, the rat has to smell the cheese. And as a nice example, Pacific Gas and Electric, the biggest investor-owned utility in the country, had on the drawing board about 20 power plants a decade ago. Today it has none. A year ago it dissolved its engineering and construction division because it never again expects to build a power plant. Instead, it now expects to get at least 3/4 of its new energy needs in the 90s met by more efficient end use by its customers. And the rest, by the way, will come from privately bid renewable sources, which are already the second best buy. If it needed a little more, the third best buy by a hair would be advanced gas technologies. But coal and nuclear are so far down the list of economic priorities, they'll never again be considered. And part of the reason for this is that the utility now has societally rational incentives. In 1992, it spent $170-odd million helping customers save electricity. That investment produced a present valued societal saving of $300 or $400 million. The customers got 85% of that as lower bills, and the utility got the rest, $40-odd million, as extra profit. It also recovered the cost of the investments in efficiency because that was the least cost resource for its system to acquire, and it was made whole for any lost revenues by a balancing account mechanism. So if you run a department of a utility that adds 40-odd million to the bottom line at no cost and no risk, you can be reasonably confident that the CEO will call you every week and say, is there anything you need? And all of the smartest people in the utility will want to work in the efficiency division to advance their careers. This is exactly the kind of cultural transformation that smart regulators want to bring about. They don't have to do it in exactly that way. There are many variations on the theme, and I think you've had a talk on this by Dave Moskovitz, who's probably our leading authority on the subject. But I would commend to your attention the principle of getting the rules right. In 46 states to this day, utilities are still rewarded for selling more electricity. So guess what they do? They follow the incentives in front of them. If any of you happen to be from those 46 states, you have a very important undone task. And people are starting to do it all over the world. Environmental concern makes it go faster, but that's not really the main driver. The main driver is a basic piece of economics, that electricity is expensive, efficiency is relatively cheap. Customers eventually figure this out, and then naturally they want to buy less electricity and more efficiency. The only question is who's going to sell them the efficiency. Over half the utilities in this country have figured out that it's a smart business strategy to sell customers what they want before someone else does, and that really their choice is between participation in the Negawatt revolution and obsolescence. As to where end-use efficiency fits in the taxonomy of options, a utility really has three broad classes of ways in which it can meet marginal demand. There are demand-side resources, grid resources, and supply-side resources. Demand-side resources include end-use efficiency, load management, service substitution, like opening curtains and turning off lights, or fuel switching. And I'll be talking almost exclusively about end-use efficiency, but the others can also be valuable. Grid improvements typically save a few % of energy, much more, however, in developing countries. And this area is driven partly by the revolutions in information systems, cheap chips, power electronics, and control theory. We will probably be at the point by the end of this decade where we can essentially eliminate stability limits in many transmission systems and just go up to resistive limits, which will be equivalent to building lots of transmission capacity without needing to, and that'll be fine because you probably can't build much more transmission capacity. But even at the distribution level, with smart metering now, you can make the entire distribution system transparent all the way into the end-use device. I have, for example, 4 meters in my house by Metrocom, which work over packet switching radio to the utility. I don't use them that way because I have a rural co-op that isn't yet that sophisticated, but they can be used that way. And each meter can report hundreds of data every 2.5 seconds, which is kind of a data-rich environment for a utility accustomed to one number in arrears every month. But the numbers are very useful because they have a resolution of something like 5 watts and 1 millisecond. It's actually fine enough resolution to raise privacy concerns. And that means that the utility can see high harmonics. It can meter real and reactive power separately and on each phase. It can do all kinds of signature recognition. We're not far from having artificial intelligence that will let the utility's computer call me up and say, We were just doing our routine monitoring of your usage patterns, and it looks to us like your air conditioner needs refrigerant and your fan belt's slipping. Would you like us to come fix them for you? And that would all happen automatically. Just the information the utility gets from smart metering is very valuable. The meters, of course, way more than pay for themselves just on avoided meter reading cost, connect, disconnect, and resolve customer billing complaints. But one of the things they do is give you a very accurate voltage reading at the retail meter level every few seconds. Southern Cal Edison found it could save 1 terawatt-hour a year of generation just by using that information to run the reactant switching at its substation so as to keep the delivered voltage perfectly flat. They knew the voltage at the substation, but once it left, they had no idea what voltage was actually reaching the customers. They had the switches, they had the capacitors, they just didn't have the information to switch effectively. Now they do. By the way, another thing they found from the first 3,000 test houses was that a fifth of them were miswired. The meters told them that a fifth of the houses had either no functional ground or ground to neutral interchange. We didn't think electrical inspection electricians were quite that bad. Supply-side resources have basically 3 categories: bulk power transfers, extending the life, efficiency, or availability of existing capacity, and new capacity. And new generated capacity falls in a whole spectrum between relatively centralized and relatively dispersed resources. The dispersed ones used to be just classical combustion turbines, but now they include a host of competitive renewable sources. In fact, there's a whole other area I won't be able to get into called distributed benefits. It turns out that resources, either supply or demand side, that come in small dispersed pieces have something like 10 or 20 major kinds of economic benefits that they're not normally given credit for, and which increase their economic value by 1/2 to 1 order of magnitude. That's a factor of roughly 3 to 10. That's a very rapidly emerging field of study. That's why, for example, PG&E recently put photovoltaics on a fully loaded substation and found it was highly cost-effective to do so because there were other benefits that could be counted in rigorous engineering economics. They were real, they were measured, they were good for the system. They hadn't been counted before, and that meant the photovoltaics, instead of costing something like 30 cents a kilowatt hour, really cost more like 8 or thereabouts. I wanted, however, to make 2 broader points from this large menu. One is how big it is. There's an awful lot of diversity, and a lot of the things in it interact. For example, the combined cycle and steam-injected gas turbines are increasingly being integrated with biomass through gasification. Fuel cells may become very cheap very quickly, which would leapfrog us into a distributed utility a lot faster than most people assume, and so on. When you're faced with such an enormous menu, the important thing is to have wise decision rules that let you pick the best buys. And the ones that most drive these investments in countries with real markets, we're moving in that direction, tend to be cost and risk. And it's interesting that in no really competitive market is significant investment taking place in the things in the lower right corner. And the basic reason is not only that they're no longer economically competitive with other resources shown, but also that they're too risky. They're these billion-dollar projects that take a decade to build. That's a bet your company decision because we live in times of very rapid technical and social change, and it's highly likely any 10-year project is going to be obsolete before it's even built. For that reason, investment has been shifting to dispersed supply, improving existing plants, better swapping the power we have, improving the grid, and most of all to demand-side resources, because in conditions of rapid change, the only ways to manage risk and uncertainty so as to minimize regret is to buy things that are small, fast, cheap, and modular. And the resources I've described that the money is in fact going into, especially the demand-side resources, meet those requirements in spades. Let me spend a while on the engineering of energy efficiency. How many engineers in the house? About a third of you. Okay, I will not make this too technical then, but I hope you'll find it food for thought. First of all, let me talk a little about mindware. Mindware is the stuff in the engineer's head that does not grow obsolete, does not depreciate, ripens with age. My colleague Liang Lok in Singapore has pointed out a very interesting calculation. From reasonable assumptions, you can estimate that a senior American mechanical engineer specifies 1,700 odd tons a year worth of cooling equipment. And that equipment will increase the utility's peak load by about 1 megawatt per year, or about $2 million a year of investment in generation and grid. Now, let's suppose that better mechanical engineering education would make that equipment 20 to 50% more efficient. By the way, that's a very conservative number. We're typically seeing 70 to 90 odd percent. We recently did an office retrofit for PG&E, saving about 97% of air conditioning energy, and it's more comfortable. But let's just say 20 to 50%. Well, in that case, by that better education, the utility will avoid a direct investment, present valued over a 30-year engineering career, of about $6 to $15 million per brain. And that does not include any saving in fuel, pollution, or the construction costs of the buildings, because there will be less and simpler equipment to put in. Well, that's pretty interesting, because that must be about 100 or 1,000 times the cost of the better engineering education. By the way, comfort will also improve for 65,000 office workers earning about $36 billion present valued. So if you had a 0.03% gain in labor productivity because people were more comfortable, could see what they're doing, and could hear themselves think in these more efficient buildings, that would double the societal benefit. But in fact, we are typically seeing in 20-odd case studies in a paper to be released at Asilomar in a few weeks, we're seeing 5 to 15% gains in labor productivity across the board in offices. Well, a 1% gain in labor productivity is economically equivalent to eliminating your electric bill in round numbers. So we're looking at a benefit about an order of magnitude more important to society than eliminating your electric bill. This flies in the face of 60 years of management theory saying that working conditions don't matter. All that matters to labor productivity is how you manage people. Well, that's bunk. Most people are uncomfortable where they work. For example, sitting here right now, as one can easily ascertain with a little scanning infrared thermometer, the radiant temperature off the floor is 20 Fahrenheit degrees lower than the radiant temperature off the ceiling, because we have these little heat factories glaring at us. Can you hear them mooing? These are little cash cows waiting to be milked. Good old 1930 technology. And you have infrared sensors on your forehead and cheeks, so when you get this 90 degrees glaring down at you, it makes you quite uncomfortable. It's as if the air were about 10 degrees F hotter than it actually is. And that's got to be a bit of a distraction. In most offices, there's so much veiling reflection off the thing you're trying to read, or the screen, that you can't read it properly, and so on. And those effects, I think, will become extremely important parts of energy efficiency engineering and marketing. But even without counting the likelihood that they raise the benefit-cost ratio to something like 10 to the 5 or 6, obviously better mechanical engineering education is a hell of a good buy. Is there any better buy anywhere? Well, I'm not sure. It's hard to think of one. Where else are we overlooking that kind of leverage by doing the engineering right? Well, the key to getting really big, cheap savings of electricity is whole system engineering with meticulous attention to detail. It is harder to do than the way engineering is normally done. Very few people teach or practice it. There aren't many experts. There are no texts or tools or time, and it's more work. On the other hand, the savings get several-fold bigger and several-fold cheaper than if you don't do it. It does often create huge spin-off benefits for quality, productivity, and so on that are very important to competitiveness. And anyway, it's more fun. I'm going to give a number of examples, I think not quite in the order shown here, but they all show the same thing, namely remarkably big and cheap savings, which often have even negative costs. Compounding savings in equipment sizing, energy, and capital cost as the equipment gets smaller, simpler, and cheaper. Even some of it goes away. And to do this takes real system optimization, not obsolete rules of thumb. And to get it done in the field takes the repair of perverse incentives. Let me start with an example from my own practice. Let's see. If we can switch over to the slides. Thanks. Okay, this is our house indoor farm and research center at 7,100 feet in the Colorado Rockies. It's a rather severe climate. It goes as low as minus 47F, minus 44C. The growing season between hard frosts is nominally 52 days, although you can get frost any day of the year. We had it last year, for example, on July 4th. It is not a reliably sunny climate. We had as long as 39 days of continuous midwinter cloud, kind of like Michigan. And during December and January, a year and a half ago, we saw the sun on a total of 7 days. Nonetheless, you can come in out of a blizzard to this atrium and you find yourself in a semi-tropical jungle surrounded by jasmine, bougainvillea, mango, avocado, papaya, loquat, passion fruit, grapes. That is a banana tree. We've just harvested the crop that came out on the winter solstice. We have another one that's ripening now that came out January 5th. I think that's we have 10 crops now. And they're really quite good bananas. Then on the banana tree, we have a number, I think 3 now, of advanced lizarding tutors that teach most afternoons. The prerequisites for the advanced course are elementary hedonism and intermediate decadence. I don't know if you all qualify. Here's Hunter holding some January tomatoes. There's a fish pond with yummy catfish and so on, and a waterfall. And then you realize there's no heating system. Well, almost none. We do have a portable supplementary heater of about 50 watts, adjustable to 100 or so. Our beautiful daughter, NARUC the Beastoid. And we do have 2 small wood stoves in which we burn, probably half a cord of wood per winter, some for aesthetics, some for backup, and we occasionally burn energy studies. But that's 1% of the heating from the wood stoves. 99% is passive solar, thanks to super windows. Super windows look like ordinary windows, but inside they have between 1 and 3 thin films, high-tech, invisibly thin coatings that reflect infrared but let light come through, and then you fill the whole thing with an insulating gas like argon or krypton. Our old version only insulates as well as 6 sheets of glass, but that's enough in almost any climate to gain net heat facing north in the northern hemisphere. Because the diffuse skylight plus the snowbound springs more energy in, even from the poleward side, than you lose. These come now in about 200,000 flavors. For example, for hot climates, there are some that are essentially perfect in letting in light without heat. So rather than using dark or reflective glass on an office building in a hot climate, blocking out most of the light, having to use electric light inside to use electricity and release heat, and then you're sort of back where you started. Instead, you can let in deep daylight without creating a cooling load of the normal sort, and then you can have very efficient artificial lighting and enormously reduced cooling loads. Somebody said our architecture here is eco-Elizabethan, but it doesn't have to look like this to work like this. You can make it look like whatever you want. It's also super insulated. There's 4 inches of foam in the middle of the walls, over twice that in the roof, so it's about twice normal levels of good insulation. And the result is that we got rid of the heating system and cut construction cost at the same time, because we saved more capital costs getting rid of the furnace and ductwork than it cost to do so. We then took the saved cost plus some more, totaling $1.50 a square foot, and put that into saving half the water, 99% of the water heating energy, which went to efficiency and passive and active solar. And also we saved 90% of the household electricity For 4,000 square feet, our household electric bill is about $5 a month at 72 mils. I know that's a lot, but this is 10-year-old technology. How do we get that? Well, for example, the refrigerator uses 8% and the freezer uses 15% the normal amount of electricity. That's also 10-year-old stuff. We're about to cut its uses in half by going to a double efficiency, no chlorinated refrigerant. And we're 95% daylit. We're not using electricity for heating, cooling, water heating, other than a little pump, clothes drying other than a little fan. So there really isn't much left, and it means you can run the entire household on just a few square meters of photovoltaics. So if, for example, I were in a country like South Africa that's trying to electrify 2/3 of the population, it would take maybe 50 years to get there by running wires all over the place. But if I made the infrastructure really efficient in the first place, then the cheapest thing to do in most places would probably be photovoltaics to go with the efficiency. And then I could do it in just a few years. So think about this as a barrel-a-day oil well. It's producing $19 a day worth of saved energy. And that extra net investment of $1.50 per square foot paid for itself in the first 10 months. Nowadays, it would be even cheaper than that. For example, now the windows are twice as good. They insulate like 12 sheets of glass. And maybe the most interesting part is that people feel better in such a building. There are a lot of subtle reasons for this. There are the curves in the building. Curves are restful. God had meant us to live in boxes. He'd have given us corners. There's natural light. There's high radiant temperature, low air temperature, high humidity, which is a lot healthier than hot, dry air. There's a lack of mechanical noise because there are no mechanicals. The sound of the waterfall, more or less tuned to alpha rhythm. The sight and smell and oxygen and ions of the plants, the taste of the plants, grab a tomato as you walk by. Good air quality because we're careful about materials, essentially no 60 hertz electromagnetic fields for whatever those do. Maybe other things we don't know about, but that's a pretty good list for starters of why, if we put our board around the table, they stay alert and cheerful all day, but if we put the same people in a room like this, they get dozy and irritable in half an hour. How about a hot climate? There's an interesting experiment some of us are involved in with PG&E. It's a 10-year, $18 million effort to figure out what is the most energy we can save cost-effectively to the utility and attractively to the customer by putting in the best integrated packages of technologies we can think of. And one of the most recently commissioned houses is a mid-range for the Davis market, 155 square meter house, where the base case we're trying to improve on in this perfectly ordinary looking tract house meets the latest California Title 24 code, the strictest in the country, which supposedly already includes everything that's cost effective at a long run marginal cost, including externalities and a 3% real discount rate. So if they did that right, we shouldn't be able to find any more cost effective savings. Well, we found some. This work was done by Dick Bourne's group at Davis Energy Group, and it's a pretty tough climate to work with. The design temperature is 105 F, 40 C. The peak temperature is 113 F, 45 C. And the normal house has a 3.5-ton air conditioner. Well, first of all, we were able to cut 23 feet out of the perimeter by taking jaggies out of the floor plan, giving it a boxier plan, and getting the same visual interest out of the roof line. We could put the windows in the right place. And Bourne's group came up with an engineered wall that has twice normal insulation, is stronger, is tighter, uses a quarter to a half the lumber, and costs $1,900 less to build. Well, so far so good. And then there were a lot of other little things. You know, saving electricity is like eating a lobster. There are these big obvious chunks of meat in the tail and the front claws. This is an Atlantic lobster I'm talking about. But then that's only half of it. The other half of the meat is tasty little morsels tucked away cunningly in concealed crevices, and you need to go after them with some skill and persistence to dig them all out. Well, we found lots of little pieces in the appliances, lights, windows, hot water system. The only novel thing, though, was dumping the refrigerator waste heat into the hot water system, which makes the refrigerator more efficient and turns it into a space cooling device instead of a space heating device, as seen by the rest of the house. And all those little things, plus the original reforms up here, saved about 3/5 of the energy, up to our cost-effectiveness limit of 64 mils. And along the way, it got rid of the furnace. Because when you had doubled, roughly, roof and wall insulation and much more efficient windows and so on, you didn't need much backup heat on the coldest nights of the year. So we got that by saying, look, we're paying for a water heater anyway. Let's just cast a radiant coil into the floor slab, and on the coldest nights, it'll be kind of like taking a shower. We'll just run a slug of hot water through the slab coil. So why need a furnace? So that got rid of $2,000 worth of furnace. But we still had 1.25 tons of air conditioning left out of the original 3.5 tons. And we were at our cost-effectiveness limit. Aha! The designers had thoughtfully reserved a special basket called Potential Cooling Elimination Package. And they had put into it all the measures they had encountered that did not save enough energy to pay for themselves. So they flunked the cost-effectiveness screen. In most programs, that would be the end of them. But wait a minute, we haven't counted another benefit yet. They also get rid of cooling capacity. And it turned out when we took those 7 non-cost-effective measures and stuck them in the design, they more than eliminated the rest of the air conditioner. Then suddenly they were cost-effective because they got rid of $1,200 worth of air conditioner and ducts. Sorry, $1,500. So actually, we ended up with bigger and cheaper savings by including measures that did not save enough energy to pay for themselves. So I'm pointing out a methodological flaw in the people normally do these things. Similarly, in our own building, of which you just saw the slides, if we had done the normal diminishing returns calculation, which we did, that said how much insulation in the walls and roof and windows and so on is worth buying, we would have stopped about halfway to where we got to, and therefore we wouldn't have saved all the money from getting rid of the furnace. You have to count capital as well as operating benefits where applicable. So by including all the measures that made sense, we ended up with bigger and cheaper savings, and we are expecting, subject to monitoring this summer, to save about 80% of the energy allowed by this very strict code for space heating, water heating, refrigeration, lighting, and appliances. Everything except the, and space cooling. In other words, everything except the little plug loads that people bring with them. We haven't tackled those yet. If you counted those, the saving would drop to 62% because those were 1/3 of the electric used to start with. What does it cost extra? About minus $1,800. In fact, about minus $3,400 because there's also $1,600 worth of present value maintenance you don't need to do on the furnace and air conditioner that aren't there anymore. So if you think about this as a supply curve of the efficiency resource, where the vertical axis is the marginal cost of saving a kilowatt hour and the horizontal axis is how many cumulative kilowatt hours you save, you stair-step up the supply curve from negative cost to zero cost to cheap to more expensive measures until you hit your cost-effectiveness limit. Most people stop there or short of there, but I'm suggesting that if you also count saved capital cost, you can tunnel through that cost barrier and end up in some lower cost. It may be up here, it may be down here. This is a schematic diagram. But in fact, we are seeing supply curves of this shape everywhere we look. Big buildings, small buildings, residential, commercial, hot climates, cold climates, new, even retrofit in many cases, motor systems, hot water systems, computer design, you name it. And it's natural enough because when all we count is energy benefits, we're missing a number of other important benefits that we ought to be counting. In fact, there's a new slide, if I can find it, that is not in your collection that makes this point even more strongly. Here it is. What are the benefits of using super windows? Most people just count saved energy, heating, cooling, air handling. Also, though, you're going to get better radiant comfort. If you're sitting next to a standard heat-absorbing glazing on the west wall in the afternoon, you're going to want to be turned on a spit and basted occasionally, because the building or the glazing will be blasting radiant heat at you at maybe 150 Fahrenheit. And that means you're going to need to blow much more cold air at yourself to feel as comfortable as if you didn't have that radiant load. So that ought to be counted, and the way you do it in modeling is to change the thermostat set point. You can often downsize or eliminate mechanical equipment with a capital cost value, as I just described. There turn out to be very important benefits to construction cost. In a commercial building, you'll save plenum height in the drop ceiling because of smaller duct sections. In a town like Washington, where you have height limits, you can actually put in one extra story within the height limit. So for almost no extra construction cost, you can increase your net rentable space by 1/5. That's pretty valuable. And the savings also in height pyramid through structural design. You save duct sections, mechanical room sizing, wiring closets that affect floor area. So you get an extra 5 or 6 percentage point space efficiency. Collectively, those kinds of benefits and others that flow from them are often worth more than the avoided mechanical capacity, which is itself a big number, 3 to 5% of project cost typically. You can get rid of perimeter zone heating by using, say, an R8 or R12 window, even in a mild climate. And we've already counted the energy cost if we did the modeling right, but we haven't yet counted the capital cost of running all that plumbing around. We also haven't counted that when you get rid of the perimeter zone heating you see along here, you're going to gain something like 5% floor space in the perimeter offices, because you don't need to worry about putting stuff in front of the radiator, and you can move things around nicely. The super windows also control UV and hence fading of finishes and furnishings and artwork. The heavy gas is a very good sound suppressant, so there's less noise. That's worth something. There's less maintenance cost because you don't get condensation on the windows anymore. It's much easier to do the entry and control of daylighting, which saves lighting energy and capacity and therefore cooling energy and capacity. And then there may be productivity benefits. You get the idea. A rigorous engineering calculation is going to count a whole lot more benefits than just energy. And some of those are really big numbers. And in almost every case, the supposedly expensive super windows, although they're not very expensive, will usually save a lot more up front than they cost. So they'll make buildings cheaper to construct. And the same can be true even in retrofit. We had a nice example in some work for then Governor Clinton in Arkansas, looking at a typical stick-built house in Little Rock, which on a hot July day would have a load shape simulated like this. And it turned out we could do a retrofit to cut it to this with a 1-year payback or this with a 3-year payback. The reason it's so cheap is we used very expensive windows. We would retrofit a super window right over the existing single glazing and therefore control a lot of unwanted heat gain, and it would save energy summer and winter. But it was the biggest contributor to the 2/3 downsizing of the replacement air conditioner. So if you did this before Mrs. Jones' air conditioner died, you'd be able to sell her a new one only 1/3 as big as the old one, and that in turn would about pay for making it over twice as efficient. So you would be able, by taking account of the interactions of performance and sizing and cost, to leverage enormous savings in energy that you couldn't have gotten just from the windows on their own. And therefore, using the expensive windows cut the total cost of saving energy in the house retrofit by about 1/3. How about commercial buildings? How about lighting, for example? Well, let's see. Here are a few slides that you don't have, but don't worry about it. About what to do in this situation. Normally, you'd use compact fluorescent downlights. There are over 500 million stupid fixtures like this in the United States. 2/3 of them or more are suited to compact fluorescence. There are over 800 different kinds of compact fluorescents on the market, more coming out weekly, sometimes daily. However, their energy efficiency varies more than 50% depending on their optical efficiency, temperature, orientation, and ballasting. Many utilities, by the way, offer rebates per socket retrofitted without rewarding good products. You ought to target kilowatt reduction with minimum requirements on power quality and fixture performance, and preferably, I would say, not just minimum requirements, but incentives for doing better. And if you have a new construction incentive based on watts per square foot, then that encourages people to use fewer fixtures of higher optical performance. And there are huge differences in optics. Here's just an example of the kinds of subtleties that come into play. If you have a typical compact fluorescent operating base up, it will hit its peak efficiency running at somewhere around the low 70s of degrees Fahrenheit, normal ambient temperature. Horizontally, it's a bit worse, but if you put it in a base down position, look what happens. The optimal temperature shifts to much lower, and you lose a lot of output, and when you're at normal room temperature, you're losing something like 12 or 15% of the output. Or to put it another way, with downlights like this, if you didn't have any vent in the fixture, you would be losing something like 12-15% of the operating output compared to just having some vent holes in the top. Because the thing will run too hot, then it also won't last as long. How about the normal tubular fluorescent troughers, of which we have, for example, 1.7 billion 2x4 foot models in this country? Well, normally one of the first things you would do is put in a specially shaped, custom designed, shiny piece of sheet metal, very shiny, which enables you to take out half the lamps, relocate the existing lamps to new positions, and get essentially the same light underneath you started with, and you have a lot of choice in how to distribute it. And it will look as if all the original lamps are still there, but it's done with mirrors. This is a new fixture of that type. How many lamps in there? Without reading the caption. What? There's only two, actually. There's one there, and there's one there, and all the rest are virtual lamps which require no electricity and no maintenance. And in fact, when you're moving the remaining lamps into new positions, that's a good time to replace them with the skinny T8 lamps that also have tristimulus phosphor tuned to your red, green, and blue retinal cones, so they're more efficient and give more pleasant and accurate color. By the way, in this Illinois building, just putting in the reflectors and nothing else led to the removal of all these lamps, each of which at ComEd rates is a $25 a year avoided electricity and maintenance cost to the operator, whose profit immediately went up by 1/4. And then when you're moving the ballast around to get it out of the way of where the lamps now are, you should put in dimming electronic ballasts, which are a kind of electronic Wonder Bread. They save electricity 15 ways. Actually 18. We've discovered 3 more since I did this chart. And I won't bother to go through them all with you because you have it in your handout. But basically, if you look at the way the savings accumulate, you find that in the middle of a building with no daylighting, you typically save about half the energy from this ballast and its dimming and occupancy controls. Why dimming? Well, because the dimming ballast pays for its dimming feature even in a core zone with no daylighting, because it will also brighten the lamps as they dim with age and dirt. So you don't need to have too much light when the lamps are young, fresh, and clean in order to be sure of having enough when they get old, dim, and dirty. It will automatically compensate for what's called lumen depreciation, and that pays for it. If you're in a typical retrofit condition where you can put dimming and occupancy controls over all of the floor space and half of it, the perimeter part, is half daylit, then you can save 70 to 80% of the energy this way. And if you get really good daylighting, it gets a lot better than that, up into the 90s%. But that's just the ballast and control savings. We're not counting yet the better lamp phosphors, and if you also make the lamp skinnier, as you should, T8 instead of T10 or 12, then that goes up to 20 or 25% saving. That is, reduction in watts per usefully delivered foot candle. We're not counting the reflectors, typically 35 to 50% gain from better optics. We're not counting reduction in overlighting, which is just as bad as underlighting, or the use of task lighting. It's virtually obligatory if you're in a computer-rich space to have less ambient light around the space, but more light from a little swing arm task lamp that you can adjust to. This isn't drawn quite right, but you can adjust it so that it lights the paper tasks on your desk and the light spills across and stops just short of the screen. You can't have more than about a 3-to-1 luminance ratio between the screen task and the paper task, or your eye gets too tired switching back and forth. But if you try to have a bright enough light all over the space to read your paper, it'll wash out the screen and you can't see it anymore. So task lighting is a very important strategy. We haven't counted other ways to reduce veiling glare. Veiling glare is when the light bounces straight from the source off the task into your eye. What lets you read is not light but contrast between, say, ink and paper. And in a typical office setting, it's about 10 times as important to reduce veiling reflections to improve contrast as it is to put more light on the task. We haven't counted the use of lighter colored finishes and furnishings to bounce light around better in the space, or ways to stretch the daylit perimeter zone. You can double or triple it just by simple tricks like top silvered blinds and glass top partitions. We haven't counted better maintenance. We haven't counted associated savings in cooling energy. This is a little artist's impression of how you can bounce light off the ceiling and then through a glass partition into the next office. You can use lighter colored surfaces. You can have an occupancy sensor to turn out the light after you leave the room and so on. That can go right into the switch box. You don't need to mess with the ceiling. There are a lot of other tricks you can do, but you see, if you're getting 70 or 80% saving before you do any of that long paragraph we just went through, you can see how you typically get 70 to 90% savings in lighting retrofit. 80 or 90 is really more like it, and the payback is typically about 1.5 years if you count the saved maintenance cost from having half as many lights and a quarter as many ballasts to replace, and if you also count the saving in cooling energy. If you didn't count those things, the payback could be about 4 years at a nickel rate. So I'm suggesting that commercial tubular fluorescent lighting retrofits ought to be a package of measures, and they'll give you the same amount of light, but it'll look better and you'll see better. We've just been through that part. On the other hand, what most utilities do and what most regulatory incentives reward them for doing, and they in turn reward their customers for doing, is a fragmented retrofit that says you can just pick out little bits of this and toss them together and somehow they'll save some energy. A lot of people are so dumb they put in just the reflector. All that did is, I mean, it'll save some energy, but it also added half an hour of labor cost the next time you have to go replace the ballast, which you should have done while you were already up the ladder. And in fact, many reflectors are not well designed, and some of them save nothing, and some of them even make the optics worse. One size fits all, and the ones that don't require optimal lamp relocation are probably hints that you don't have a good reflector. Many people, 99% of those using electronic ballast, use dedicated non-dimming ballast. That cuts the savings threefold. And you'll only get 3 or 4 kinds of saving and lose 14 others. And then you have to go back and retrofit the ballast later. Many people don't change the lamps, so they get bad color, not many lumens per watt. The need to change the ballast twice because T8 ballasts are different than the fatter lamps use. And again, you'll be duplicating the lamp changing labor. Many programs still incentivize the 34-watt so-called energy-saving lamps, a completely obsolete technology, and you shouldn't use them. Many people leave out the controls. Again, you have to retrofit them later. You're slashing the savings. It's hard to move the space around because you don't have the control flexibility to tweak things to meet the new layout. It's very hard to meet the video display terminal standards without dimming controls. But those kinds of measure-by-measure, slice-and-dice utility package rebates encourage fragmentation rather than integrated packages. And you'll find that all over the industry. Let me make one even more basic point, that retrofitting the light fixture in the ceiling starts at the wrong end of the problem. Because the efficient lighting equipment is useless if it lights the wrong place or at the wrong time or at the wrong angle, so the task contrast is washed out by veiling reflections. The logical sequence for saving lighting energy and seeing better works like this. You start with the task. First of all, for example, if you have a photocopier that's giving blurry copies that are hard to read, you fix the photocopier before you put on more light. Then you improve the space. For example, if the light is indeed bouncing from the source off the task into your eye, and you have veiling reflections washing out the contrast, move stuff around. If you have discomfort glare reflecting off your computer screen because there's some bright luminance back there, move stuff around. Move the desk, move the screen, move where you sit. Bounce light better in the space. Improve lighting quality. Much more important in general than lighting quantity. And then optimize the quantity over time and over space. Most of our offices in this country are still lit between 50 and 100 foot candles. Anyone want to know, anyone does know by chance, the recommended, officially recommended optimum ambient light for typical computer-rich office spaces? 5? What? 5, almost. 7.5 to 20, roughly, foot candles, depending on the age of the people and the difficulty and importance of the visual task. Now, more than that on task is often desirable. On the paper task, you may want 20 to 50 foot candles, but 50 is very unusual. That's basically for people who are quite well along in years, who have a difficult and critical task. Maybe they're doing fine needlework or something like that. Most people setting lighting standards don't really understand about lighting quality, and what they're interested in is how many foot candles it says on this meter. But foot candles tell you nothing about quality. You can actually see much better with 20 glare-free indirect foot candles bounced off the ceiling than with 100 glary foot candles of downlight. And the meter doesn't show that critical difference. Moreover, most people assume that the old Illuminating Engineering Society standards everybody uses are minima. They're not minima. They're meant to be optima. It's at least as bad to have too much light as to have too little. And if you look at how well people can see versus how much light is on a task, there are very rapidly diminishing returns, and we're way out here. If you go back a ways, you might have a barely perceptible or indeed unmeasurable few percent loss in visual performance, but enormous energy savings. And I'm not suggesting you should actually do that, but you may want to do it. You ought to think about it. And you can get the same result often 10 times as easily by adjusting lighting quality as increasing lighting quantity. Also, notice I said over time and space. The part of an office, say, where you actually need to do critical visual tasks is typically about this big. How about all the rest of it? The time when you need to do them is typically very small. How about all the other times? Would you control an enormous building's temperature with one thermostat? No, because there are different people with different needs doing different things at different times and places. So you try to give local control. And the same thing is true of lighting. The next step would be to harness and integrate daylighting. And there are ways now to retrofit daylighting that goes way into a building, as far in toward the core as you want. Only after you've done all that stuff do you improve the lighting equipment and controls. That's what we call lighting retrofits. That's what most people start with. But it should be step number 6, not number 1. And after that is improving maintenance, training, and management, which are quite important. I recently saved $40,000 a year in one facility just by labeling the light switches so people could tell which switch went with which light. Yeah. Commercial buildings. I happen to start with lighting because it's the biggest load in commercial buildings typically. But just to show what's possible, here are some existence proofs. In terms of site energy, that is the energy delivered to the building rather than how much it took at the power plant to make it, a typical office 11 years ago used 123 site BTU per square foot year, but over 100 large monitored offices built in the early 80s were already cutting that in half. The best codes typically cut it by 2/3. And just to show that whatever exists is possible, here are a number of offices that beat that figure by a factor of at least 3, and in some cases much more than that. And these are all measured except this, which was simulated, but the measured value is better than that, I'm told. And you notice that here are some with pretty difficult climates, like Brisbane, Australia, which gets very muggy. Same for Tokyo. It's basically a Houston climate in the summer. And what's interesting about these is these were mid-80s offices before we had super windows for hot climates, before we had most of the modern lighting and office equipment options. We were still getting these enormously large savings in cost-effective and pleasant buildings. So that suggests that there's an awful lot you can do to buildings. What would you do to retrofit a big office? Well, we've had a number of projects lately, PG&E and others, both new and retrofit, confirming cost-effective savings in the 3/4 range. And typically to do that on retrofit, you will use tuned super windows. What does tuned mean? It means you have windows that look the same on all the different sides of the building, but on each elevation you optimize the spectral properties of the window. They're the same in the visible spectrum but different in the infrared. So you might want more heat gain on the north and less on the west and so on. And because you can now independently control the flow of heat and the flow of light in each direction, you can simplify controls, downsize mechanicals, and greatly improve comfort. And we now have windows that are twice as good in letting in visible light as in letting in total energy. That's as good as you can get because half the sunlight is visible to start with and almost all the other half is infrared. Deep daylighting, supplementary lighting of the kind that I described where the connected load is 0.6 or 7 watts per square foot, but as used it's only about 0.3 because of the control savings, and indeed with good daylighting that goes down to about 0.1. In contrast, the recommended ASHRAE standard these days is about 1.5. So you can see we're down by a factor of roughly 5 to 15 below that, depending on the degree of daylighting. Plug loads I'll get to in a minute. We cut from the usually assumed 5 to 8 watts a square foot, or the actual less than 1, down to about 0.2, just by picking the right office equipment and operating it in its power management mode. No loss in functionality or productivity, no extra capital costs. Works the same or better, costs the same or less. And if you're doing a new office building, it's actually worth buying a whole new set of office equipment so that you can take the capital credit for downsizing the mechanical systems of the building. And then we can use a small, super efficient mechanical system. It doesn't have to be all refrigerative either. In fact, a retrofit design done recently for PG&E is 0.14 kilowatts per ton for the whole system. Normally you'd consider yourself doing very well at about 1.5 kilowatts per ton. The existing rooftop units were 2.0. So that means you're getting out 25 units of cooling for each unit of electricity, and that's about a 97% reduction when you combine it with the fact that we cut the cooling load in half. It'll actually be a 98% reduction when we get through turning over the stock of office equipment. Well, here's an interesting retrofit case that I'm working on right now. It's a large curtain wall office near O'Hare Airport. It's 20 years old, which means that the glazing units are already starting to fail, and a frost test says they'll essentially all fail in the next 6 years, which is during the lease period. And you don't want to have to annoy your tenants by going in to replace windows all the time. So they need to reglaze the building as they're leasing it up now. And also the mechanical system's going to need replacement. It's 20 years old and it has CFCs. So you have to do something about that. Well, it turns out if you reglaze this glass curtain wall with super windows and put in the efficient lights and office equipment, then you can cut your 750 tons of cooling load to 200 tons, and at the same time you can almost quadruple the efficiency of the cooling system. Predicted energy saving is about 3/4, over $1 per square foot year. That's in a market where people fight over rent differences of 5 or 10 cents per square foot per year. Predicted payback roughly -5 to +9 months. Huh? Well, that's because we're going to have to reglaze it and replace the mechanicals anyway. And when you take account of the downsizing and simplification that come with reducing the cooling loads, you find it costs about the same to renovate the building with good stuff that'll save 3/4 of the energy and make it more comfortable as to retrofit it with the same lousy stuff that's already there. A few designers actually do it that way, but you can teach how to do it. And the main reason it's cheap is that you're shrinking the mechanical systems by several-fold, because they're about 1/4 of the total construction cost of the building. You're also avoiding future costs for CFC change-out, because you do that at the same time. And if you have to replace old glazings anyway, double glazing only lasts 23 years at best, then it's especially cheap. Now, in new buildings, the extra capital cost of doing the stuff right and having a 3/4 or more saving, 80 or 90% is more common, that extra cost is negative. You'll typically cut 3 to 5% off the total construction cost of the building. And that's even after you pay the designers more for working harder. You can count about $3,000 a ton as a round number for avoided mechanical system cost. Now, let me just say a word about the plug loads, because that's the fastest growing load in the fastest growing sector. You don't have this chart, but don't worry about that. On a summer day in a large office, typically the load up here is for cooling. That's air handling. That's water heating, cooking, and refrigeration. That's inside lighting. What's this thing at the bottom? That's the plug loads, the stuff you plug into the wall, which is mostly office equipment. Now, let's take a little closer look at that curve. You see how it just rises up during the middle of the day? Here's a Canadian measurement of it. That's the on-time, the electric load for the office equipment. But the amount of time it's actually in use as measured by keystroke activity is the lower curve. Notice about 90% of the area under the upper curve is just idle time, where the machine is sitting there not being used. Great power management opportunity. In fact, there are gadgets you can retrofit, not just gadgets but also software, which will automatically power down different parts of your computer and printer and monitor and stuff that you're not using, and then they spring back into action when you need them. Well, that's just the beginning of the savings, because you can also use efficient chips and efficient drives and so on. So you end up with something like this that runs for 9 hours on a 5-ounce battery or on 4 AA alkalins, and this is a fairly powerful 486 using 1.5 watts. Why does this matter? Well, each watt per square foot of heat released in a typical, not very thoroughly occupied office costs you 1/10 of a ton of cooling, directly and indirectly. That's worth about $3,000 to the owner. So 1 watt per square foot raises capital cost by about $1 per square foot. Now, if you have a full suite of modern office equipment and you believe the nameplate ratings, which are higher than actual use by a factor of typically 2 to 5, then you might convince yourself that if people are packed head to tail with olive oil, 100 square feet per person, you'll have 5 watts per square foot. Most mechanical engineers assume something rather like that when they're designing the building, because they don't want to be sued for making the cooling system too small, and they're not paying for it. Actually, you have about 1 watt per square foot, and even less than that when you count the fact that not everything is on at the same time. Now, if you have identical functionality, same or lower capital cost, and buy the right stuff, and you can even have a laser printer, but it will have modern power management that turns off the fuser when it's not in use, or you can use an inkjet printer if you want to save a lot of capital cost. You will end up with about 0.2 watts a square foot. What difference does that make? Cuts about $5 a square foot off the project construction cost. That's 6 or 8% of the total cost of building the building. That's 10 or 15 times typical competitive rent differences. And by the way, if you were going to use 5 watts a square foot as assumed for the office equipment, you would save enough electric use to buy the building, more or less. These are very large numbers. These will get any real estate developer's attention. And indeed, I recently did a little analysis of what a desktop computer can save if you buy an efficient one. That's only a moderately efficient one. Well, it saves direct energy, air conditioning, standby and operating losses of an uninterruptible power supply that many offices have, so you don't lose data if there's a lightning strike or something like that. You can avoid some distribution wiring losses. Altogether, you save the best part of $100 a year worth of electricity, and maybe a bit more with demand charges. So over a typical 6-year cycle life of a computer, that's about $500 present value if you're using an uninterruptible power supply. Capital costs. Well, there's air conditioning, UPS, wiring, utility investment, $500 to $800 roughly. And if you needed upgrades to the building, as many have needed and still need, for wiring or cooling, especially because of harmonic currents from lousy computer power supplies, that's anywhere from a few hundred to a few $1,000s avoided. And environmental benefits and possibly productivity benefits. You get the idea. It turns out there's somewhere between $1,000 and $3,000 societal saving per efficient computer when you add it all up. Most people don't add it all up. Here's another way of putting it. The building owner and operator will save on the order of $500 or $600 if the building does have good power quality, adequate cooling, and adequate wiring. The utility will save about that much or more. You also save a lot of pollution, and you may recover some lost productivity. In new buildings, the capital cost savings can easily double. If you have cooling, wiring, or power quality problems, they can increase manyfold. Those are big numbers, and that's just for one computer that doesn't even cost extra. That's why utilities in your areas ought to be encouraging everybody to buy Energy Star, voluntary EPA standard computers with the features implemented, and indeed, even better than that. Why doesn't it cost extra to make this stuff? Let's take the most efficient, sophisticated PC on the market that isn't a portable, not a battery model, it's a plug-in model. When the manufacturer was designing it to use 5 or 10 times less electricity than normal, the first thing they noticed was that the power supply was a real dog, and they came up instead with a little sort of cigarette pack sized power supply that was very efficient over a wide range, had great power quality, but it cost a few bucks more. And the bean counter said, wait a minute, you can't spend that on the power supply, or we can't compete in this cutthroat market. But then it turned out that the power supply got physically smaller. They could use a smaller case. And more interestingly, it didn't need a cooling fan anymore. And that meant there was no fan noise, so you could now market it on ergonomics. Except now you can hear the little mosquito-like whine of the hard drive, so now we'll put in anti-noise to get rid of that, because you already have the loudspeaker and the chip, so anti-noise is basically free. You don't have a forced airflow through the machine anymore, so you don't have a dust path through it, and it runs cooler and it's more reliable. You can stick it in your desk drawer so people don't walk off with it. Surprisingly, the whole system gets cheaper because you save more on things like case and fan than you pay extra for the power supply, and it's also more marketable. Back to commercial retrofit design strategy. If you've rigorously avoided the heat gains from things like office equipment, lights, water coolers, coffee machines, and you have a really efficient envelope with all the neat things that an architect can do to it, then you can have much smaller mechanical systems to the extent you still need them. And you can end up Under 20,000 site BTU per square foot year, that's about 5 times to 10 times less total energy than typical modern office buildings. A few kilowatt hours per square foot year. If it's retrofit, typical payback's 3 to 8 years if you don't need to replace glazing and mechanicals anyway, and more like 0 if you do. New construction, nearer 90% energy savings with lower capital cost. And a magical building with terrific amenity and aesthetics, which means it's easier to get and keep tenants. They have lower occupancy costs, you have lower operating costs, so you have better net operating income, better residual value. This is the language that real estate developers speak, and it really does get their attention. Now, why isn't it all done that way? My favorite mechanical engineer says the mechanical engineering standard operating practice, we'll call it a Aesop fable, is take previous set of drawings, change the project box that says which building it is, submit drawings to client. Building is constructed. Client gripes of discomfort. Wait for client to stop griping. Repeat process for 25 years, at which point you're an experienced designer and probably have some ASHRAE awards. Well, I don't want to be unkind because there are indeed some honorable exceptions, but this irreverent summary is pretty close to the bone. And basically what's happening is the clients are getting what they pay for. They're paying for plain vanilla or worse. They might, if with a really conscientious designer, get vanilla with almonds, but they will not get Rainforest Crunch. Basically what they're paying for is infectious repetitis, not real optimization. And more fundamentally, what's going on is not just inadequate fees, but the structure of the fees is utterly perverse, because architects and engineers get paid a fee which is based directly or indirectly on the cost of what they design, not the savings, the cost. You typically start at 6% and negotiate downward from there. Now, if I'm a mechanical engineer and I get 6% or a bit less of the cost of the equipment I spec, which is big, complicated, and expensive because I'm doing it the way I just described, then I can just about make a living, because it's 6% of a big number and I'm not working very hard. On the other hand, if I work half again as hard and do real optimization, that is hard work, my fee goes down if it wasn't already fixed, because the equipment is getting smaller and simpler and cheaper, and a lot of it's disappearing altogether. And if the fee was already fixed, I'm still doing a lot more work for the same fee that was barely adequate to start with. So either way, my profits go negative. That's a hell of an incentive. How would you fix this? Well, one way would be to educate designers to bid and clients to demand a two-part fee. Plain vanilla for ordinary design, plus if you do something smarter to cut the life cycle cost, we'll give you X% of whatever you save. So give the design team a piece of the action. Or utilities can fix this problem. In fact, we persuaded Ontario Hydro to put in a design rebate that pays directly to the design team a rebate equal to 3 years' worth of energy savings against, say, ASHRAE baseline. You could pay half of it up front and then half of it a couple of years later trued up to the actually measured savings. So the designers have a strong incentive to see their intentions fully carried out all the way through construction, commissioning, operation, training. Now, this is part of a much broader problem. My colleagues at eSource, our technical information service, now publish 6 volumes, which I initially wrote the first 5, of technology atlases. And the one we finished in '92 was called The State-of-the-Art Space Cooling and Air Handling. It showed how to save 80 to 90% of air conditioning energy, and after the break I'll say a little more about that. And it was very cost-effective stuff to do, entirely reliant on established engineering principles that just weren't being properly applied. And then when we got through with it, we said, wait a minute, that's an awful lot of energy. How much investment has this country already misallocated to air conditioning equipment and power supplies to run it that we would not have spent if we'd built the buildings right in the first place to achieve the same or better comfort? Answer, approximately $1 trillion with a TR. And then we said, wait a minute. This is a market economy. How can we have misallocated $1 trillion just in one end use? So we did this analysis. It's called Energy Efficient Buildings, Institutional Barriers and Opportunities, another eSource paper, in which we looked in considerable detail at how buildings are conceived, financed, designed, built, operated, maintained, leased or sold, and occupied. There are about 25 different parties involved. Each of them speaks a different language. They can't communicate. There's no Rosetta Stone. They hardly have occasion to communicate anyway, because the design process is so utterly disintegrated. You know, the site planner will typically pick the big building envelope, and then the architect will sort of make it look pretty and make a one of these all glass and no windows solar ovens. As a matter of fact, you often nowadays have two different architects, one doing the shell and one doing the core, as if they weren't related. And then the architect will toss the drawings over the transom to the mechanical engineer and say, here, cool this thing, shoehorn your equipment in somewhere. And then the ME tosses it over the transom to the electrical engineer and says, here, power this thing. Who tosses it over the transom to the constructor and says, here, build this thing. And eventually somebody hands you the key and says, here, run this thing. It's nuts. You couldn't imagine a process better calculated to produce buildings that use about 10 times the energy they should, are less healthful and pleasant to be in than they should be, cost more to build than they should. And then you look at the incentives seen by each of these 24 parties. They are perfectly perverse. Each of these parties is systematically being rewarded for inefficiency and penalized for efficiency. So guess what we get? Now this is a complex institutional problem, and we have $12 trillion more or less worth of obsolete buildings out there that will need to be retrofitted. That's also a complex problem. But there's no way out really but through it. And we are finding some very encouraging trim tabs in how to correct these perverse incentives. I gave you two examples of how to fix the problem for the architects and engineers. Well, that's 3 down, 22 to go. And any one is potentially a showstopper. But there are some very helpful concentrations of power in the industry. For example, all big commercial real estate projects in this country have fiduciary money in them, pension funds, insurance companies, and so on. Their investment is controlled by a very small number of real estate investment advisor firms. I think the number is something like 25 of those firms control 78% and 50 control 94% of all the fiduciary investments in commercial real estate. And these are very sophisticated competitive advisors. They watch each other like hawks. If you get the first few, you've got the rest. So we're now identifying and starting to work with the early adopters in order to get them to swing that whole market. Then there are people called lenders' counsel who have to sign off on the loan documents. If a certain kind of energy performance is on their due diligence list, it happens. Otherwise, the loan isn't approved. There are errors and emissions insurers one has to talk to. You know, there's a long, complicated list of actors, and one has to take, I think, a fairly sophisticated view of how to affect their incentives. But I think it is already becoming very obvious that if we do pay attention to those incentives, we can, over time, get the kind of engineering practice that I've described put into actual buildings. If that happens, we will find that utilities need to spend a lot less money on hardware. It's, in general, a lot more cost-effective to put your money into soft costs than into hard costs. Soft costs are things like design. And New England Electric System has already rejigged its commercial sector efficiency delivery program design in order to concentrate precisely on correcting perverse incentives. Let me show you one graph here about why that matters, then we'll take a actually 2 graphs. Then we'll take a break, and then we'll come back and talk a little about one more technical area, which is drive power, and then some concluding items, and then I hope a protracted discussion. Here we are. This will just give you an idea of where the money goes. Following the money is usually a good advice. For a typical 15-story office building put up new in the United States a couple of years ago, the physical construction and design cost is half exterior, interior, and structure, a quarter mechanicals. This big wedge, 9% of the project cost, is the space cooling and air handling equipment. The engineer who specs it gets that little tiny wedge, 0.6% of project cost, as her fee. Let's look at the operating cost. Well, I mean, first obvious conclusion to draw is you can pay that engineer a lot more, and more than make it up immediately by cutting the cost of the system. Okay, so capital cost will go down by trading soft against hard costs. Here's the operating cost of the same building. This is national average information. This is what we pay to the people who work in the building. And in many industries, it's a lot more than this average. That's the rent. The net operating income, by the way, is under $5. That's what the owner is sentimental about. That's the energy bill, the electric bill, the repair and maintenance cost. The space cooling and air handling system's energy and maintenance cost is down there, and that's what we pay the people who run the building. Now, notice that this little smidgen down here that's for building operation and running the comfort systems, those are the 2 most important determinants of how productively these people work and whether they want to stay around and keep paying the rent. So there's enormous leverage because this number is 100 times or so, over 100 times these numbers. In fact, it's almost exactly equal to 100 times both of them put together. And in fact, the present value of the salaries of the people who work in this office is approximately 1,000 times what we paid once to the engineer who designed those comfort systems. We're spending our money on the wrong things. We ought to be putting a lot more effort into designing it right in the first place and then operating it properly, and a lot less into having to pay people to fight against their working conditions in order to try to be productive, and a lot less also for the capital cost. Well, I hope that gives you a little to mull over as we take our break. We'll start at 10:30 sharp and have discussion at the end. Thank you. I have some papers here. Thank you. I have some papers here, and you can catch me in the break if you have a particular interest in reprints.
Can we have it?
Please don't just raid the